Okay, I'm going to use the board, but I'll start over here in case anyone comes in late so they can see the announcement. No, it's okay. I have to start on one side or the other. So it's modeling fixation probabilities and extinction probabilities this afternoon. I'm hoping to do maybe just half the time that's really teaching, and the other play around with the probability generating functions and take up the questions, and it'll be a bit more relaxed because these days are very long, I know. The basic idea is that we have a de novo. There are many variations, but this is an easy way to start to think about it. A brand new mutation occurs. And again, for starters, I'm going to talk about beneficial mutations. So let's assume for the moment that it's beneficial. And it probably occurs in a single, well, it definitely occurs in a single copy when it first appears. Sometimes that's not true in bacteria. Sometimes they can make two copies at once of the first beneficial mutation, right? And then here's the picture that you've seen before. If that's the allele frequency, the beneficial mutation might occur and then get lost because of drift. These bumps are drift, right? And get lost again, and then eventually, one lucky time, it might actually get to a frequency where it can rise to fixation. And if that happens, this would be kind of equally bumpy. Here's fixation. Down here is extinction. Sorry. And just throughout the lecture, to make it easier, I'm going to use pi for the probability of fixation, which will save me writing probability of fixation a lot, and I'm going to use big X for extinction. And obviously, pi is 1 minus x, right? But sometimes it will be more convenient for us to use one or the other. Okay, so as Brian pointed out, in fact, you did that example, right, last night, where you needed this to happen 43 times, I think, or 48 times on average. 44? I'm not very good with numbers either. Before this happened, right? So usually, even when the mutation is beneficial, it gets lost. So how can a deleterious, well, let's say a neutral mutation, how can a neutral mutation ever fix? Do you have a sense of that? Drift, yeah. If we're in a small population, that's the other answer, exactly right. In a small population, these bumps are going to be really big, right? And you could actually bump up to one at some point by drift. And same for deleterious mutation. It can fix by drift. So there are two classic approaches to studying this problem mathematically. And I'm going to talk about, okay, everybody got this message? I'm going to talk about branching processes first, because they're a little easier to wrap our heads around. Then I'll talk about the other approach, which is the diffusion approximation, and then we'll go back to branching processes when we play around and do some math ourselves. So one is branching. And this is Haldane's approach. To this problem. So you imagine, the idea here is you have this beneficial mutant, and we're going to keep track of its offspring. So maybe it had 2, and maybe this one had 1, but this one had 3, in the next generation, and then in the next generation, and so on. That's what we're sort of keeping track of. And so we modeled the individual, their children, which you thought about last night, I think, their grandchildren, and so on. And in ways that we will work out together, there's a really powerful and elegant result in branching processes. We're going to derive it, which I'm excited about. It's actually like one of my favorite lecture topics to give. It works out that if we define the offspring distribution, so that's just like the table that was on the board for the tutorial, right? You define the offspring distribution for the initial individual or mutant. And if we assume, this is a big assumption, right? Assume it stays constant as the generations go by. So if this guy is a mutant, this girl is a mutant, her daughters are also mutants with the same offspring distribution, and her granddaughters are mutants with exactly the same offspring distribution. Okay? So under those assumptions, we can compute the ultimate extinction probability of the lineage. And I will convince you of that later. Okay, so what's wrong with this? Can you think of any reason why the offspring distribution wouldn't stay constant? There's no genetic change in these individuals. Sorry? Environment. Yeah, the environment could change. Great. Yeah, frequency dependent, I think, is the most important factor probably. So as the mutant population grows, the fitness of the population is increasing, right? And only relative fitness matters if you have some kind of resource limitations. So the selective advantage of the mutant is effectively going down over time, right? As there are more and more of her cousins in the population with her, right? So this is a pretty strong assumption. The main reason that we can use this is that we make this assumption that the population size is really big. Yeah? Yeah, okay, so the question was, can I clarify again why frequency dependence would make a difference? So you have, suppose the mean, well, in fact, the mean of the offspring distribution for the wild type is 1, and for the mutant is 1 plus s. And this is when there's 1 over 2n of the mutant and 1 minus. So that's the frequency of the mutant, and that's the frequency of the wild type. Later on, when you have like 50% here and 50% there, then half the population is having this, has this fitness. The mean population fitness, sorry, not doing a very good job explaining this. Your fitness is going to be your fitness over the mean population fitness. Yes, the relative fitness of the mutant is going down. Okay, so if there's some resource limitation, distribution. Yeah, okay. So imagine we're resource limited, so there's a constant population size. Okay, so we can only maintain a constant population. If your relative fitness goes down, So you do agree that the relative fitness goes down? Yeah. So before, let's say at the beginning, the wild type was having, well, let's call it 1 and like 1.2 at the beginning. Then these wild types are having actually less than 1 offspring survive, right? Their relative fitness is less than 1. Later, when we're at 50-50, this relative fitness is much less than 1.2. Yeah? At the beginning, it's almost 1.2. Later, it's much less than 1.2. And this has to be the mean of the offspring distribution. No? I think maybe we'll come back to it. Okay. Sorry. So, assume n is large. So, maybe I've got these a little out of order. Sorry, my terribly unprepared lecture here. If you assume n is large, really large, then at the beginning, for the first few generations of this lineage, the individuals don't interact with each other. That's the big assumption. So there is no frequency dependence yet, because there's only 10 of us in a population of 1 million, right? Then there's no frequency dependence. And all the mutants are individuals. They're all independent. So if this is true, this is not heinous. We're okay with the constant offspring distribution. Yeah. And as it turns out, when beneficial mutations go extinct, and you can simulate this yourself, it happens early on. So almost all the extinctions that happen in the first 1, 2, 3, maybe 10 generations, and then it's all over. If you've survived 10 or 15 generations, you're probably going to survive. Right? And so this is not as bad as an assumption as it seems, because extinction is largely determined in the first few generations after this mutant arrives on the scene. So, I wanted to say, I love branching processes. I love this approach. I find it really intuitive. I love it so much, I'm going to put that on the board. It's really intuitive to model each individual and their children and their grandchildren and then look at whether the lineage goes extinct or not. It's a really nice way you can explain what you're doing to people. But it has a few big drawbacks. As we said, it's only accurate at the beginning of the mutant lineage. But luckily, as I said, that's when extinction happens. And there's another big drawback. So as we said, as you said, neutral and deleterious mutations, they can only fix by drift, right? So if a population is really, really large, what happens to drift? Does it go up or down? It goes down, right? And in fact, in the infinite limit, it goes to 0. So if there's no drift, what happens to a deleterious mutation that arises, or a neutral one? It's gone, right? So this approach will not tell you ever that a deleterious or neutral mutation will fix, right? So for S less than or equal to 0, deleterious or neutral, this approach gives us that extinction equals 1. Okay, so we need another approach. But, don't worry, we're coming back to this one. So 2 is, as promised, the diffusion approximation. And this one's Kimura's approach. He did tons and tons of work extending it to various cases, but I think Malako did it first. There's an accent on there. Do I have it in my notes? I have one like this in my notes. Kimura. Okay, so the disadvantage of this approach is that you don't model the lineage explicitly. Instead, you start right away by looking at the frequency. So what we're going to keep track of is the frequency F, say, of the mutant allele. Which starts at, if it's de novo, let's say it's a diploid, 1 on 2n. But actually, even though it could really only be 2 on 2n, 3 on 2n, 4 on 2n, we're going to let f be any real number. Okay, so we do this continuous approximation. We allow f to be a member of the reals. Is that okay? Any real number. Okay, so I've actually made a really similar assumption in a different way here. What do I need in order to make these little pieces all be small enough that I could approximate f as continuous? You see what assumption is built into that? Yeah, it's a big population size again. Yeah, exactly. And large enough. Those little steps are small. We'll say that this assumption of continuity is close. Assumption is okay. Something like that. Okay, and the basic idea here of this and any diffusion approximation and related, so if you have physics training, it's Fokker-Planck, or if you have stochastic processes training, it's backward and forward Kolmogorov equations. Same idea. So we have an idea of, we know how f tends to change. In some little interval of time. And we also know how the variation in f changes in delta t. So if you start, for instance, here at f0, we know, based on, for instance, selective advantage of the mutant, that at time delta t, actually, let me move it out, even though it's really small, f tends to move up to here. And if we looked at time 2 delta t, we'd expect on average that f is bigger. Okay. But we also know, for reasons that I'm not going to get into today, we can work out how the variation in f changes with time. So really there's one f value here, but here we don't know what's going to happen. It's a random process. So there's a whole distribution of possible f values here, which come out of the board, but I'm going to draw them, I'm going to flip them down onto the board. So there's a possible distribution. And at this time, there's a whole other distribution of possible f values. Is that clear? Okay, except they don't look quite like that. I'm going to draw again. For the cases that we care about, again, Newton frequency, here's delta t, 2 delta t, here's f. But I'm going to draw a wider distribution so you can see. Okay, see that? Now, what if I integrated the area sitting right there on that curve? It's extinction, yeah. This is the probability that after delta t, the mutant was extinct. You get it? And then if you do the next one, it's going to be even wider. Probability that it's extinct at this time is the area under there. Yeah, that's based. I think the most important thing I can give you is this intuitive sense of how the diffusion approximation works. Okay, and the other neat intuitive thing we can get just from pictures like this is that suppose I have, let's compare this beneficial mutant with this beneficial mutant, X, and X has a smaller S value. So it's climbing, but more slowly. But suppose X also has a much reduced variance. I need like colored chalk here. There's like a little teeny tiny filled in bit under this curve. And then for this X, there's only a little tiny probability of extinction. All right, so just from these pictures, you can get this sense that there's going to be a balance between how beneficial the mutant is, how fast it increases in the population, but its variance in each time step will also determine its fixation probability. Okay. We haven't talked about it yet. So that's a great question. So what's causing the variance in the distribution? It's ultimately, if you think about the offspring distribution, you can have a probability of 0, 1, like we did last night, probability of offspring. And if you, for instance, always have one offspring with probability 1, there's 0 variance, and then you would get, I don't know, the round circle case with 0 variance, and you'd never go extinct. And you can see that you're never going to go extinct, right? But if, more realistically, you have some 0s and some 2s, you'll go extinct with some probability. That probability is completely dominated, by the way, by this value right here. And if we add a bit more variance, how could we add variance? We need to put some more guys out here. In fact, the only way to add variance, this is actually important, turns out to be important mathematically, to make this distribution vary more, sorry, we can't really add things out in this direction. So this guy's coming down. Why am I not liking that at all? I want to compare guys with the same mean, though. I need to bring this guy down and this guy up to keep the mean the same. So there's a distribution with very wide variance as compared to the one that just had 1, right? So these distributions set what the variance is going to be. Yeah? That's true. That's true. Thank you. Did you guys hear that? For what I said about P1 equals 1. This guy that he could never go extinct, that's only if he's haploid, if she's haploid. For the diploid case, extinction is still possible here. Okay. So we use this to estimate extinction, and I'm going to like skip math, skip, and give you the solution. As I said, I think the important thing is the intuition. So the solution to this diffusion approximation, you see it in a lot of different forms, and as I was complaining at lunch, I can never remember which way it goes, but one form is like this: 4 S P N E negative 4 S N E. That's the probability of fixation. And that is for a diploid. Over the course of this course, you're converting me to complete deep diploid examples, almost. The heterozygote has fitness 1 plus S in this formulation, and P is the initial frequency. I guess I should have just made it, let's not make it P, because I've been using F0. Okay, so that's probably just a lot of symbols. Let's try and talk about it a little bit. The first thing to note is that this guy is really pretty small and drops off fast. So for example, if you have S is 0.01, then when NE is around 100, already this is basically 0. So the denominator equals 1, and we can ignore it. So if you're working with small populations, you need to care about this denominator, or if you're working with great big selective coefficients. But for a lot of practical cases, the denominator just becomes 1. And since it will be easier for us to develop intuitions, I'm just going to talk about that case now. So if that's true, we get pi is 1 minus e to the negative 4 s f0 ne. Now, which way did I want to simplify it next? I guess the other common thing that we think about is we already talked about how the frequency of a de novo mutation is 1 on 2n. And then we get something, it's increasingly simple here. 1 minus e to the negative 4s 1 on 2n ne. Negative 2s ne over n. And then furthermore, in the simplifying situation where the census size is the same, do it this way, as the effective population size, we get 1 minus e to the negative 2s. And there's even one more simple thing we can do. Do you know this one? The one more simplification is S is small. We always like to say what happens, S is usually small. If S is small, we can Taylor expand here, and the fixation probability is 2s. Okay. So I think no, maybe I haven't said yet. These are so chalky. It's a little better. So unlike branching processes, that solution that I gave you, that works even for neutral and for deleterious. This whole approach works for neutral and for deleterious mutations as well. So you can treat all the cases. The branching process, we started with a single individual. But here we simplified here, but we could start with any starting frequency, right? So it's a lot more general and applies to many more cases. And that's redundant. And I wanted to tell you in particular, well, do you need that in your notes? Are you taking notes? To what extent should I write this stuff that I'm just saying on the board? Is it useful? Nod, don't care, shake, abstain. Yeah, okay. Yeah, okay, furthermore's over the top. I'm so used to writing for undergraduates who are like, I'm going to study from this. Okay. Then I won't write what I just said. Oh, the other thing, so it works for deleterious, it works for neutral, it works for different starting frequencies. It works for long times. Remember, I also said the branching process only really works at the beginning. But this, you can follow the diffusion approximation right up until the mutant frequency gets close to fixed. Right? So it's very much more general. No, the whole thing is called a diffusion approximation. Right from, yeah, so that's a good question. Right from where I said, even though we know the frequency of the mutant has to be 1 or 2 or 3 over the whole population size, but we're going to let that be a real number, that's like the approximation part right there. These last ones are like simplifying approximations of the diffusion approximation. Why is Yeah, it's okay. So like if you started with a bunch of molecules and they diffuse, yeah, it's Brownian. It's the same thing as the frequency. It starts at a certain point, and then because we have this whole distribution of possibilities, it diffuses kind of. It moves around randomly to one of those, and then it moves around randomly to the next one. Yeah. Yeah. Oh, I'm glad you asked that. Let's go back to the first one. I think I even have this. I have this written. Okay, so this is great because I'm going to take this back and use this at home. For the neutral case, we need to start with this. -4 S F0 NE S NE. And you want the limit, sorry about the chalk, S goes to 0. And you're going to get 0 over 0. And then what do? L'Hopital's rule. Yeah, that's why I'm going to take this home because it's like a real-life application, not a made-up one for my textbook of L'Hopital's rule. We have to use L'Hopital's rule, and when we get there, I'll leave it as an exercise for the interested reader. You will get to P. And now I'll give you the intuition about why you get there. This is like, you can push the symbols around and you'll get, oh, sorry, you won't get P. You'll get F0. That's what we're calling it. Okay, so you push the symbols around, you get F0. Why do you get F0? I think actually we already heard from Brian why you get F0. Yeah, you could Taylor expand too. Yeah, you get exactly the same thing. But you wouldn't get to use L'Hopital's rule. So, at the beginning of time, when this mutant appeared, this guy was the mutant. And these are all her sisters and brothers, now that I'm moving over to the diploid camp. We'll have diploid sexuals. And you can make the argument that if you wait long enough out to here, the population at this time has a common ancestor if we go back far enough. but I'm actually going to do the reverse thing. I'm going to wait long enough until one of these guys is the common ancestor of everybody, right? Wait. And then somebody here, 1 was the common ancestor. But if s equals 0, from the eyes of diffusion or drift, from the eyes of evolution, these guys are all completely equivalent, right? So what's the chance that this guy is the common ancestor? 1 on 2n, right? So, and in fact, if you had a different frequency, though, suppose we were cared about some population where there was 4 on 2n individuals, the probability that one of those was the common ancestor would be 4 on 2n. Right? So the probability of fixation, oh, I promised I could just use pi for that, equals the initial frequency. And since we talked about briefly about deleterious or about neutral, we can very quickly talk about deleterious. If you just do the math, you get that you will see that the probability of fixation is going to decline close to exponentially. As well, I mean, as s moves to the left, as the magnitude of s gets bigger, but s is negative, right? So let's say for more deleterious mutations, and if we put it all together, you get a picture like this. Maybe I just need a new piece of chalk. So when s is 0, for a mutation that first occurs in a single copy, here's the fixation probability. This is 2s, that line, and then way up here, actually, this isn't really to scale. Way up here, we're going to saturate at 1. And down here, you have something that's, well, it's got to be smooth, but exponential decay, right? And don't make the mistake. I've made this mistake, actually. This region is kind of confusing because you know that the 2s approximation is good when s is small. But when s is super, super tiny small, that's going to be even less than the neutral fixation probability, and you can make the wrong prediction here. Okay. So more good questions or bad questions? Really, I'm good with either. All right. So now we can play a little bit with branching processes. So maybe if you have your, whatever you were working on to do the problems, if you have those handy, you can look and check your answers. Did anyone do like 11? Keeners? Oh yeah, good. Excellent. And did anyone like get stuck on 3, 4? That wants to admit it? Yeah, okay. When I was circulating around, people were like making steady progress on it and understanding, and I hope it'll help you follow the magic to come. So I think everybody could plot the probability mass function. We don't really need to review that, but I'm going to put the numbers up here so we can remember. Actually, no, I'm not going to put the numbers up. I'll just quickly sketch. Look like this. And I think the expected number of offspring was a harder question than some of the others. P0, P1, P2, P3. Well, actually, those are here. Anyway, P4 is plotted there. And the expected number is we get 0 this fraction of the time, we get 1 this fraction of the time, we get 4 this fraction of the time, and you should have got 1.65. And I think when I was going around last night, everybody had that. That's good. The probability generating function, you just plug the numbers in. So you should have something, again, I think you all know this, 0.2 plus 0.3x plus 0.25x squared, and a couple more terms. Okay. And then the next question was, what is f if you evaluate at 0? Bless you. And this was a kind of insulting question, right? So you all know that's 0.2. But less insulting was, what's the biological meaning of this? Yeah, so it's the probability of having 0 offspring. Okay, so here's another question. Suppose I gave you a completely different probability generating function. So I rewrote the table. I now have offspring numbers that go up to 100. And then I wrote the probability generating function h of x of that and evaluated it at 0. What would the biological meaning be? Same, yeah, probability of 0. And this is going to be important later. You're going to forget this, and I'm going to ask a question later that you need this piece of information for. So tuck it away. Whenever you put a 0 into a probability generating function, you get the probability of 0 offspring. Okay. And then f of 1 is 1. Yeah, you're all over it. And again, I do another PGF of a different distribution, and if I evaluate it at 1, what will I get? 1. Exactly. Good. Always. Because you get the sums of the probabilities. Okay, good. Next question was the derivative. So this is another great, this is a high school calculus question, I guess. Take the derivative of this function with respect to x. And you got 0.3 plus 2 times 0.25 times x. I'm going to do one more. 3 times, what was the 3? 0.15 x squared plus a few more terms. And what was the next question? Is it positive or negative? If x is positive, always positive. Yeah, let's just think. I'm going to stop saying that. Let's just say x is always on 0, 1 for the rest of the lecture. So it's positive. And if I had a different probability generating function, would it always be positive? Yeah. And what about the second derivative? Always positive. And the third derivative? Always positive, right? There's nothing but positive numbers in there. Yeah. Okay, so why do I care about that? It's for the sketch. I think a lot of people may work with probability generating functions. Maybe not a lot of people. Anyway, I worked with them for a long time before I actually drew one, plotted one. And I think actually the geometric intuition, even though the function itself, as we said last night, is just a clothesline for storing numbers, the geometric intuition you get from plotting it is helpful. Okay. 0, 1. So for this PGF, the bits that we need were in the previous little questions, right? So where do I start here? 0.2. Yeah. Well, x is 0, y 0.2, yeah. And my slope at 0.2, what's the slope always? Positive, yeah. So it's actually only teeny tiny bit positive, I might add. And I'm going to go through when x equals 1. I'm going to go through 1, 1. If I had a different probability of 0 offspring, this is going to move. And the slopes are all positive, connecting these guys. Concave up or concave down? Concave up, yeah. Everything positive, positive. The first derivative positive, second, third, fourth. Zoom. Okay, so that's basically it. And pretty much all PGFs look kind of like that. Okay, what was next? F1. Oh, F prime of X evaluated at 1. We did F prime. Now we take the derivative and evaluate at X equals 1. Why would we care about this? We get 0.3 plus 2 times 0.25 plus 3 times 0.15. And did anyone get that far? 1.65, excellent. Which happened kind of coincidentally to be the average number of offspring. And what if I had a different PGF? Can you see this? Can you see why you got the average? Unfortunately, I've erased it now, right? But when we computed the average, the mean number of offspring, we had 0.3, we had 1 offspring this fraction of the time, and we had 2 offspring this fraction of the time. We got the same thing, right? And we can do it symbolically to show that it's always going to be true. Because we have P0 plus P1x plus P2x squared. Then F prime is going to give us P1. And like differentiation magically takes this 2 and puts it down here where we need it. 2P2x, 3P3x squared. And then evaluating at 1 gets rid of all these x terms conveniently, and we're left with the average number of offspring for any PGF. And this is the sort of thing, so I talked about this last night, how mathematicians don't like to work with that table of values, probability mass function. We'd rather work with, yeah, it is a mass function, but we'd rather work with continuous functions because we can do cool things like differentiate. And it just so happens that if you store the numbers, the p's, in this particular way that you do in a probability generating function, then all these beautiful and really useful and in fact powerful properties are packed into this function, and you can manipulate it in different ways and get stuff out, like you can take a derivative, evaluate at 1, and you will always get the mean of the distribution. And I'm going to show you a few more of those properties and then show you how we use them to get extinction probabilities. Okay, still good? So, kids and grandkids was the next bit, and we were going to use an easier generating function for this. 0.5 plus 0.3x plus 0.2x squared. And I think first I asked what's the meaning of the 0.2 or the 0.3, can't remember. So what's the meaning of the 0.2? Yeah, you guys are all over it. Excellent. So you can go both ways, right? You can go from the table of values to the generating function. You can go from the generating function to the table of values. Probability of 2 offspring. Okay, and I asked you to tell me what's the probability for an individual who has this generating function and whose children have the same generating function. What's the probability that there are 0 grandchildren in the lineage? Okay, so there's a few different ways you could get 0 grandchildren. All right, you see that? So I'll tell you one way of getting 0 grandchildren is just not to have children, right? So the ways to do that is to have 0 children. Okay, what's another way to have 0 grandchildren? One, yeah. So you could have 1 child and then 0. Or you could have 2 and each of them has 0. Right, and then we just work out the probability for this process. So, and it's like this is a possibility, or this is a possibility, or this is a possibility. And we need this and that to happen, and we need this and that to happen. So that tells us how to put the p's together. So probability of 0 grandkids is what? P0? What else do I need? P1, P0, yeah, and then P2, P0 squared. And did anyone do the probability, for instance, of 1 grandkid? .15. Oh, yeah, you really did do it. You went right. Okay, yeah, I'm not going to actually put in the number. That's probably right. So you can not have 0 children. You could have 1 kid or 2 kids. And here you need to have 1 grandkid. And here we've got a couple cases. One of them, 1, 0, 0, 1. Yeah? I see lots of nodding, so I think you're good with this. So we need P1 squared plus 2P2, P1, P0. Yeah, which is 0.15? Yeah, okay, good, thank you. Okay, we won't go on the board. You'll be happy to hear. Maybe, well, you know what? I'm just going to put the 2 case up. I'll put the answer up because I want to compare it to something later. P1, P2, 2P2, P1 squared, 2P2 squared, P0. Okay. So now I will show you another really neat and very useful property of probability generating functions. So you can just watch. What does it mean if I do this? So symbolically, it means everywhere there's an x. In g of x, I now put in g of x again, right? Functional composition. So it might have been a while for biology majors. So our old g of x, maybe I should put that up there. Let's just do it symbolically. P0 plus P1x plus P2x squared. So now wherever there's an x, we put in g of x. Which is P0 plus P1 times P0 plus P1x plus P2x squared. Actually, let's just do that g of x that only has 3 guys because it'll make our lives easier. P2x squared and P2 times g of x all squared, which is a little bit of a mess. Let's just do it like this. Okay. Someone asked me last night, is there like an easier way than to compose these probability generating functions? And I said, no, composing them is the easier way. The hard way is drawing all the possibilities. So I'm going to now collect like terms and write it like this. We should get the constants. There's a P0, there's a P1, P0, here's a P2, P0 squared. Those are my constants. P0 plus P1, P0 plus P2, P0 squared. And now I'm going to collect terms that multiply x. So the first one is this P1 squared x. And then over here I will have, for example, a P2, P0, P1x, etc. And those terms end up looking like P1 squared, like I said. We get two P2, P1, P0 terms. And here we get P1, P2 plus 2, P0, P2 squared plus 2, P2, P1 squared, or the coefficients of x squared. And then we actually do have some more terms now that we won't do. Okay, so do you see? Yeah, you guys are like nodding, pointing. You see this correspondence? That we have this is what we derived was the probability of 0 grandkids. And then there is the probability of 1 grandkid and the probability of 2 grandkids. So this whole thing, if you have the probability that there are 0 here, and you have the probability that there was 1 in front of an x, let's use like big P for the grandkids. Then this guy, you see that is itself a probability generating function that describes what in words? The number of grandchildren. Yeah, exactly. So we get that g of x is a PGF for the grandkids. Number of grandkids. Okay, so what's the probability that there are no grandkids in this lineage? Yeah, evaluate this at 0, this bit, or just P0. We already know that. Yeah. So it turns out, this is like proof by example. It turns out that we could prove, but we won't here today, that this is kind of generally true. If you keep composing, you could keep going more generations. So if every time there's an x here, you put in g of x, and you expanded the whole thing out again, you'd get a probability generating function for the number of great-grandchildren, and so on and so on, right? So let me get that up here. So generally, g of x is itself a probability generating function for the number, let's say, in the lineage after, let's compose n times, after n generations. So what do I want to tell you next? So what is, let's go back to F. We'll just be more general. So we have our beneficial mutant with probability generating function f of x. So if I wanted to know after a long, long time, how many mutants are there in the lineage? I would do f of many, many f of x's. PGF, number in the lineage. I'm going to even say ultimately. If I could like do this infinite numbers of times. Okay, what if I evaluate at 0? Remember that piece of information in your back pocket? Pull it out now. It's extinction. It's the probability that there's 0 individuals in the lineage after a long, long time, right? Because this is a PGF. Any PGF, when you plug in 0, you get the probability of 0 guys in the lineage. So f of f, it's the probability of extinction. Basically, it's our big X. Yeah. Is everyone good with this? Okay, so now I'm going to do something that maybe is not clear that you can do to both sides of an equation, but you can. I'm going to take f of both sides of this equation. So I'm going to stick this value in as an x, and stick this value in. So I get f of. Okay, some of these pieces of chalk are squeakier than others. Let's try again. F of 0 equals f of x. Right? And like this is a number, and this is a number. So f of the number has to equal f of the number, right? So, but I already had like an infinite number of compositions on this side. So what happens if I compose it one more time? It's the same, right? Exactly the same. So this equals this. And this equals this. This equals this. And this equals this. And so this is, we've now reached like this beautiful, powerful result I keep talking about. I have f of x. So physically, what that looks like? Why did I make you sketch the curve? It looks like this. Here's f of x going to 1, 1. How do I find the point f of x equals x? It's the intersection, right? Right here. So this you could think about like, I should have written that down below. This is y equals f of x, and this is y equals x, and that's the point where they intersect, right? X. It's also x over here. Okay. So now I have in my notes, this is an amazing and powerful result. So what's amazing to me about this is that to find this fixed point, called a fixed point, to find that point we just need little f of x, right? We don't need to compose it a gazillion times, right? We don't need to do anything except find where it crosses this line. So what I'm saying is that given only that probability table, the table of offspring values for the very first, well, and all subsequent mutants, but for the mutants, just given those values, you can plot this curve, you can find where it intersects that line, and you can predict that at infinity, the lineage. I think that's so cool. Right? It's so powerful that you don't have to go and look at the children and the grandchildren and the great-grandchildren at all. You just look at one offspring distribution, right? The very first bunch. So we only need f of x to find big X. Yeah? Questions? No? It's good that you're discussing. That's awesome. Okay. So Haldane used this, basically. And here I'm going to do a little extra math. And Haldane used our favorite offspring distribution. So I'll give you one guess. You get 3 guesses and only the first one, how does that go? 3 guesses and the first 2 don't count. For what probability distribution Haldane assumed for his offspring distribution? Poisson, yeah, exactly. So he used the Poisson distribution. And for that distribution, P0, P1, P2, let's say with mean lambda, anybody remember what these look like? You mathematicians? Yeah, that's good. E to the minus lambda is here. And then we've got another e to the minus lambda. Lambda, yep. And e to the minus lambda, what have we got? Lambda squared on 2. E to the minus lambda. Lambda cubed on 3. These are really factorials. Okay, so let's build the probability generating function because it's kind of cool that Haldane used. So the PGF has got to be e to the minus lambda, lambda e to the minus lambda times x, lambda squared e to the minus lambda. Actually, it was better the way we did it over there. E to the minus lambda, lambda x, e to the minus lambda, lambda squared, x squared over 2, e to the minus lambda, lambda cubed, x cubed, 3 factorial, da 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 da. If I pull out the e to the minus lambda terms, 1 plus lambda x, let me do this to help you out, lambda squared, now let's do it this way, sorry. It'll be more clear like this. Close bracket. Okay. Math geeks, what's this? E to the lambda x, yeah. This is, in fact, by definition, e to the lambda x. It's not an approximation there. E to the lambda x minus 1. Okay, and this is another reason why probability generating functions are convenient, because instead of the whole Poisson distribution like this, it's all really captured. The whole probability generating function, even with all of its x terms going out to infinity, can be written just like that, all right there. Yeah. And so if we take the mean to be 1 plus s offspring, then we need to solve x equals f of x, e to the 1 plus s, x minus 1, x minus 1. And when you do that, which I won't do in front of you, you have to do some, it's really fun to try to get the 2s out of this. So when you do that, you get The extinction probability is 1 minus 2s. And this is Haldane's famous, you've seen it already, right? That the fixation probability is 2s. Famous result. For those of you that want to try it at home, you have to do some Taylor expanding, but you want to take the lawn first and then do it. I think that's the trick that you need to do. Okay, questions about Haldane? Okay. Yes, the Taylor expansion, I think it's s squared that you stop at. But yeah, that's what it implies, that you, at some point, you neglect either the s squared or the s cubed terms. It's probably the s squared terms because we only end up with one s, right? So yeah. Okay. So that's actually all I prepared. So we can have a little break, I guess, or we can take more questions. Okay. Oh. Yeah, so well, I could go on and on, as you know, about that. So the question was, what else can you do with branching processes? How do you relax assumptions? Not sure where I would start. So you want to, one thing you can think about, this is actually a great way for me to tell you some more. So you know how we did one generation and the next generation and we composed? It's actually more general than that, in that if the individuals go through one stochastic process, like having offspring, but then a different stochastic process, like being sampled in serial passaging, to pick an example close to my heart, you can also just compose those PGFs. So for example, if we had, losing it, G of x is like the number of offspring after growth, G for growth. So you have a population that grows, and each individual here has a certain probability distribution of offspring up here, and we're going to put all of those p-values into G and build a probability generating function. And then if I have B for bottleneck of x, so for all of these individuals that exist here, of them I'm going to sample fraction d of them. So they survive with probability d to get into the new founding population. So this is like they're having offspring. There's a bunch of guys here, and they either have 0 or 1, daughters in their lineage, which is themselves here, right? So can you tell me what the probability generating function is for this offspring distribution? There's only two possibilities, right? They either have 0 or 1 offspring between the beginning and the end of my sample. Yeah, so what goes here? Well, what goes here? D, yeah. And then here, yeah, exactly, 1 minus D. So now if I start with a single guy here, and I wanted to know what's the probability distribution of this bacterium, say offspring, when we get to the beginning of the next bottleneck, or the beginning of the next growth phase in the new founder population, it's like there's offspring, and then this is like offspring, and we can do that same grandchildren composition trick, and it actually is G of B of x. Confusingly, it actually works out to be in this order. even though mathematically you kind of like to think of the thing inside as happening first and then the thing outside, it goes like this. So G will be a PGF itself of the offspring right here. Okay, so what's the probability? Is this too hard? What's the probability that ultimately, after a whole bunch of serial passaging, the lineage is extinct? That's maybe a big jump to make. What's the probability distribution of the lineage here, right after the second bottleneck? Yeah, I think I'm hearing it. G of B of, yeah, beautiful. And you see you've got this thing repeating, and you could keep going, and you could keep going, and then we could do the whole trick again. We could evaluate at 0, and it would be the ultimate probability of extinction. So you just need to find, I do it over here, G of B of X equals X, and you've got the probability that bottlenecks make you go extinct. And you do this for all kinds of processes, right? Stochastic processes that the individuals you care about are undergoing, and compute extinction probabilities. You can, and it's messy. It's not a nice thing to compute. It's a really good question. The question was, can you calculate the mean time to extinction? You can approximate it, but there's not a really simple, elegant approach to it. Yeah. Yes. Yeah. Exactly, yeah. So you can delve into the whole first passage time literature. That comment was, would it be like a first passage time? And that's exactly what it is. Okay, I'll say one more thing, which is that in my experience, my limited experience doing this kind of thing, what my group has found is that extinction probabilities in particular are really, really sensitive to tiny details of the experimental protocol, to things like whether bacteria can have 3 offspring or not. And so I think it's important to get the right model for your experiment and your model organism if you're interested in computing these. You have to pin down the details pretty carefully. Like 2S is not universal. Yeah, Chlamydomonas. Okay. I've never seen that. That sounds really interesting. I haven't seen it. Yeah.
So is the population size constant here? The branching? And then is it
The population size, the wild type population size is constant and very large in the branching process. So remember all the stuff that came before? I introduced branching processes and then did the diffusion approximation, then we came back to branching processes. All those assumptions apply to all of this stuff. So we can only do beneficial mutations. We can only do large population sizes. But large doesn't have to be that big.
So where did we use the constant assumption?
Oh, where did I use the assumption that it's constant? Well, it could. What you assume, really, the only assumption you use is that the mutant offspring distribution doesn't change as the generations go on. So you could, if that's possible in the context of the wild type population fluctuating around. You know, it doesn't have to be constant. It has to sort of not affect, the mutants have to not affect each other, can't be frequency dependent.
What happens?
But I think your intuition is really interesting, though, because actually we don't even think about the wild type. And if you simulate these things and you want to get an accurate estimate of X through simulating a branching process, you don't even simulate the wild type. You just need to have a mutant, and she has her children and her grandchildren, and you look at how often the lineage goes extinct, and you don't care about the 2n-1 wild type that are doing whatever they're doing. You don't include them. They have no effect on the branching process.
So what if it varies, like cycles of, does that matter? Will it change things?
Yeah, absolutely. And there are papers, I think Saliato has one of the main, and I think it's Otto and Whitlock, actually, but Mike's gone, on a series, so a population size that changes in a sort of cyclic way, or goes up and comes down, goes up and comes down, or has any repeated pattern. Yes. Yeah. Yeah, I don't think so. But I'm not like, I'm 95% sure that you need to have a finite mean, but I'm not 100% sure. Okay. Thank you. Oh. Galton. Yeah, yeah. So there's a Victorian polymath, Galton, who wrote this letter in the Chronicle of Higher Education about he was concerned with the extinction of English surnames. So he cared that he was worried or concerned that the upper class English surnames were going extinct more often than the lower class English surnames. And he wrote a letter in like the scholarly journal of the day describing this problem and asking if anyone could help him solve it. And then Watson, who was a preacher, a man of the cloth, they came together and they worked out this problem, and they were the first ones to develop branching processes to look at the extinction of those important English surnames. So it's also called, in stochastic processes, it's called Galton-Watson process. And he did lots of other very cool things, Galton, actually. He discovered plant species. You know, these Victorians, they did it all at once.